hopefully.
Okay.
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 Yeah, sorry for the browser bar, but yeah, that's unfortunately not something. So, okay, let's give it a go. Right. Okay. So, well, my name is Francesco. Tonight, I'm going to talk about, as Zainab was saying, turning FP theory into team superpowers, so that teams can use FP in order to improve and become more efficient. So the reason, what is it showing? Okay. Yes. So the reason for this talk is that I like to stand on the shoulders of giants. Then it's very nice to be on building on top of someone else's knowledge as well as experience, because it makes, first of all, my job easier, and also it makes for answering questions such as what is FP, or how do I do FP, or where do I do FP, it's just easier to answer. And also, like, it's an honor and a pleasure to have one of the giants tonight in this room. Knowing it's one of those knowledge I built my knowledge in the course of years, anyway. And the agenda for this talk tonight is basically just going through two main things. So we'll start off with some FP theory, and then we will talk about my approach on how to apply this FP theory in a team context. So first of all, let me start with some perhaps outrageous claims. What FP is not about? Well, essentially, FP really is not about libraries, it's not about frameworks, it's not about category theory, it's not about monad, it's not about using flat map or fold and so forth and so on. That's got like very much nothing to do with that. FP is perhaps way more than that. And also another claim that I want to make is that FP is really not hard. It only requires a mindset shift compared to like what people are typically used to when it comes to starting a journey into FP, perhaps from a more imperative or object-oriented kind of approach or way. And I wanted to share this very nice story coming from this book that I'm showing on this slide, which is called Functional Thinking by Neil Ford, which is the story of a lumberjack. So imagine that you are a very efficient lumberjack in the woodcutting industry, and you are very good at using your axe for cutting woods, right? And then at some point, a seller comes in and tells you everything about a new tool, the chainsaw, right? So it tells you about how way more effective you can be with it, and then manages to sell you one of these chainsaws. So you eventually, after having purchased this chainsaw, you go in the woods and you try and cut down trees by swinging vigorously this chainsaw at the trees, but of course you get nothing out of it, right? Because that doesn't work like that. So after some times, then you just dismiss this chainsaw as just a fad, and you go back to your well-known axe until instead someone else comes in and just explains you how to crank chainsaw, right? So that's really what we will try to do tonight. Then we'll try and look into how to crank, or what it takes to crank this chainsaw. But before we can start doing it, we need to discuss a bit the first principles. So we need to start from first principles in order to dive a bit into the ideas behind FP, or at least what it takes to get there. So let's start, first of all, by talking about some fundamental and foundational concepts behind software engineering, let's say, or system designers. So these are like the first principles that I want to talk about. So modularity, composability, and emergence. So first of all, is there anyone in the audience that has an idea of what modularity is, or what it means? As a concept, as an idea. Any wild thoughts? Guesses?
Legos.
Legos. Well,
The composability?
Yeah,
Well, it's further.
I'm trying to
start first.
describe it without saying composability.
Exactly. Yeah, that's the bit of a difficult part, right?
More independent.
Yeah, well, yeah, exactly. That's exactly that, right? So modularity is effectively the problem of designing subsystems or components that can be used in a variety of contexts. That's in a nutshell what modularity is, right? But then, as you guys were also saying, because you all are like very well-versed functional programmers, of course, you're all also immediately thinking about how to compose these modules, right? And that's where like composability comes in, where the value of a software engineer's job really comes from, right? As in your wages as a software engineers are paid because you are composing together modules. You are composing together stuff that does other stuff, right? So this is where essentially the value of composing modules together comes from and goes. And then we have this interesting concept of emergence, which perhaps is like a slightly trickier idea, which is actually it's an idea that comes, I think, from evolutionary biology. But it's been borrowed into the field of system thinking and system design. And emergence is the characteristic of a system being more than the sum of its parts, which means that in order to be able to understand a system when a system is emergent, you need to have the full picture of what the semantics of all the components of the system have in order to then understand and predict how the system is going to behave. So it's rather typical for a system to be emergent. One observes an emergent system when composing its modules together, but perhaps these modules, for example, might be acting either in a unexpected way because perhaps they are doing more than what they are promising its users to do, or perhaps because they hide some extra bit of behavior that is not really described, perhaps even like at type system level. So, for example, when it comes to throwing exceptions and so on, right? So this is where FP comes in and tries to offer a solution. Enters compositionality. The compositionality essentially, in a nutshell, is the idea of composability but without emergence. So, for example, when you compose a module, you understand fully the semantics of some module, and then you compose this module with another module of which you fully understand the semantics of, and then you get a whole system out of this composition, then because of this propriety of compositionality, then you get to understand the whole system zooming in and zooming out without losing precision on the semantics itself. So we can zoom in applying a deconstruction process to the smallest implementation detail without losing precision in the understanding of the behavior as well as the meaning of the code that we're looking at. And how do we achieve that? And this is like the second part here, where compositionality requires, to some extent, local reasoning. So the ability of reasoning about a block of code in isolation is what local reasoning is. In the ability of looking at some piece of source code and immediately understanding what that means without having to refer to anything else within the system, which means that you can then analyze and change in isolation, perhaps a piece of software, without having to refer to any external phenomena or any external factor in order to then be able to safely, in a way, change or understand or adapt or integrate the piece of code elsewhere. So the code, in order to be compositional and to allow local reasoning, effectively has to become self-contained as we said, not dependent on external factor, and do precisely what it declares, which is like the other fundamental part on the picture here. For example, we can look at the snippet of code here where we have a add function that declares that you can take as input two integers and it returns another integer. So that gives you the ability to locally reason about what's happening in the function, or the concat function that allows you to concatenate two strings, or the two-employee constructor that allows you to build an instance of employee by using two instances of one of a person, one of a company. And all this effectively allow you to have a clear and transparent understanding of the meaning of these functions. Whereas instead, if we look at a function such as divide, then that kind of function doesn't enable local reasoning, because even if on the tin you see that it takes two integers and returns an integer, effectively, you're not guaranteed to get that back, right? And I'm sure that everyone knows that if the double I operand is evaluated as 0, then you know that you will get an exception out of that. Which means that then out of the divide function, what you get is a break in the ability of locally reasoning about the code that you look at. So let's recap what we've been seeing so far in order to then proceed on, right? So as good functional programmers, what we want to do is when we start writing some code is to start by building perhaps modules and then compose these modules together and to achieve the goal that we set out to, as we were discussing before. But then we also have the opportunity to control emergence, making our systems compositional by making use of local reasoning. Okay, so this is effectively in a nutshell where and what FP can give us, what functional programming can give us on top of what we've learned and what we've done probably all up to here. Now, this is where like the second part instead starts, where we talk about the how and where, which is like my take on how this idea of FP can be applied on a day-to-day within some team that wants to use FP techniques, right? And I've come up with this idea of this classification of 3 different tiers, which are going to essentially classify a set of techniques based on what is the FP maturity, quotes, of course, of the team that is using them, as well as how big is the size of the project or the projects on which these teams are working on. So a tier 1 of techniques for teams that are more new to FP and or the size of the project is small. Tier 2 instead for a medium FP maturity or for medium-sized project, and tier 3 instead when it comes to teams with better confidence with this kind of techniques and also larger projects. So let's look into, first of all, the techniques that, for me, will play in a context of a tier 1 team or a tier 1 project. So first of all, seeding control to the runtime, then using refinement types and new types, enforcing non-empty collections, making use of total functions, and also using unit returning functions only for side effects. So, the idea of seeding control to the runtime essentially boils down to making sure that you are not trying to do what the runtime is already been specialized for, right? So, for example, typically the first example is just using a map function on any collection, such as a list, which essentially means, of course, don't just write your own hand-rolled for loop, but instead just use a map function which has got like the logic which is already ingrained within the runtime and takes away a lot of like possible missteps and mistakes that could be done if otherwise it was done by hand. But at the same time, for example, one could decide to use a function such as map filter, which takes a function that goes from A to option B, instead of using, for example, a combination of filter and map calls, right? But also like even more sophisticated examples, such as using something like group map reduce, where you can use that function instead of chaining together group map values on reduce, which, by the way, also gives you back a more efficient algorithm implementation instead of just calling together these three functions as well as map filter, because map filter does exactly the same, right? So it improves on the complexity of the implementation. Then we move on to using refinement types and new types. So for me, using these two kinds of types is a very quick win, an easy way to give precise semantics to the values that are in your code. So this is like just an example of like, again, building a simple person object that uses as parameters a age object and a name object, but these are just wrappers around some integers and some string, but effectively these attributes are characterized by a very precise semantic, which is enforced by the use of a refinement type library, such as the refined library for Scala 2, where, for example, in order to build an instance of a person, it doesn't make sense to have a age which is negative or a name which is an empty string. So by using these techniques, effectively, we are narrowing down the surface of possible mistakes or even bugs due to the fact that if we use instead base types or primitive types that come from the JVM, then the ability of picking a wrong value for this kind of attributes will be like way easier. Instead, like this way, we are just restricting the pool of possible values that can be used. And for completeness, I'm also putting in the same implementation using Scala 3, which I feel is a bit more convoluted in a way, because the approach here will be to use opaque types, which compared to like using the new type notation that comes from the new type library for Scala 2 is a bit more clunkier in a way, but nonetheless, it's just a minimal overhead. You know, it was pretty much the same outcome. Then enforcing non-empty collection. Well, this idea really builds on top of what we just discussed, right? As in, it's still a technique to refine, to narrow down what are the semantics of the values that we are dealing with. So in this case, if you have a method such as inserting into database only if I have something, which takes a non-empty list of DB records, that guarantees that that method is going to be called if and only if you actually have something in memory in order to be inserted into the database, which essentially means that you are improving not only in the semantics of your application, but also in terms of like executing all the things that really make sense to execute. Otherwise, you just skip altogether a step like the invocation of this method here. And then, well, tying back to what we were discussing before, enforcing the use of total functions, where, for example, the divide functions that we were discussing before is not defined for all the values of integer because of the reason we discussed, right? But a function such as divide can be rewritten in such a way that it can become a total function by considering that int, the int type, can also have a value of 0, which means that taking that into consideration, we can make the divide function turn an optional integer rather than just an integer, which makes then the semantics and the meaning of this function completely defined for all possible values. And last but not least, for this tier, unit returning functions should essentially only use for side effects when it comes to perhaps just pulling together stuff that does something else, but then you don't want to return nothing out of that, which means that effectively, by using a function that return unit, you are essentially telling your consumer or your user, I don't really care about like the value that I'm giving back to you. And this is like what you should get out of that. And this is like really what also like the meaning of unit is. Saying unit, much like void perhaps or nothing in other languages, really represents the fact that I don't want to give anything back because there is nothing really relevant in terms of value to return. And the example here is by composing together functions that in turn do something, but at the end of the whole execution, there is really nothing relevant to return to my caller because I've done my job. And therefore, this function says or tells my user the only thing that I care about doing in the body of this function is just to compose the other functions that I'm using. Then let's move on to tier 2, in which these techniques actually I didn't mention earlier are suggested for teams that are more confident with the using the techniques that we are discussing, but typically a team that sits comfortably within tier 2 perhaps should also like really looking into using all the techniques that are in tier 1. So effectively they build incremental. So for tier 2, my suggestion is that the team should try and focus in avoiding Boolean weakness, using and enforcing the command pattern, using functional error handling, and also programming against the interfaces. So when looking into avoiding Boolean blindness, what I mean by that is that, for example, say that you have these 3 modules, which are like here exemplified as object A, object B, and object C. So in object A, you have some function that extracts some values out of the database in the shape of a Boolean. So you have like a true or false out of the execution. Then in object B, in a different module, you use these, you collect the value that is generated, is returned by the invocation of this function, which is still in a Boolean. And then in a third module, perhaps like far away the code base, then you make a decision based on the value that is being returned, that is being collected within the module. So what's the tricky part here? Well, essentially, the problem is that in order to understand what is the meaning of the condition that led to execute or not, whatever is the decision that's being taken in the third module, it requires you to track back the meaning of the value returned by the method in package A, which means that essentially you have to, again, go back to be in an emergent system where you have to understand the whole system as a whole in order to have a precise grasp of the semantics of what you're doing in the third module here, right? So in order to avoid that, typically using ADTs is a possible and perhaps like the most effective approach, where instead of using just a naked, just a plain Boolean, you can describe a ADT that gives you all the information that you need down the line, even far apart from where the Boolean or the condition this case, gets generated, so that wherever in the application a decision is made based on that value, there is no doubt, there is no uncertainty or ambiguity around what is the meaning or what is the trigger that eventually makes you execute whatever is the call at the end of your chain. And because of that, because of the fact that we're using ADTs, then we can also nicely pattern match against that, which means that you can also ingrain within the type system the understanding of the semantics and then trigger consequently the execution based on the understanding you are expecting in the dedicated pattern match block. Then using the command pattern, well, this is really just an extension of what we discussed so far, right? As in, when you use the command pattern, you essentially build ADTs that give you all the semantics and all the information that you need in order to then be able, down the line within a chain of calls, to perform some operation which is encapsulated in its meanings within the data type that is described. And again, there is no ambiguity around what is the intent of the initiator of some execution, some chain of execution, so that, for example, in the slides, whoever is executing do something, then is giving out a specific piece of information, a specific command to then the consumer, so the apply command function that is going to perform then a very specific operation based on the command that is receiving, with the extra benefit that also, given that we are dealing with ADTs, then the instances of the ADTs can also carry all the information at once of the things that need to be done without having to go back again to other parts of the code base in order to understand, in order to apply the logic it calls. So this is precisely the reason why this is an extremely powerful technique. And also using functional error handling. So by just looking at a function such as the making method that we have there, where we try and turn a arbitrary string into an integer, and instead of just like throwing an exception, we can encapsulate the exception or even like transform the exception into a specific error data type that then can be unequivocally interpreted as a error if it is an error by, for example, in this case, wrapping it into a left so that we can handle the possible errors or the possible success in a consumer function such as handle int or error, which has the ability of then forcing the caller to deal with the error. So this is like the extra superpower that this technique gives us. The fact that there is no way in which any error condition or any error scenarios can slip through the net. You can't like simply ignore the fact that you are getting an error. You are forced to deal with the error, which increases precision again in the intent and the meaning of the program that you are building. And then for tier 2, last but not least, programming against interfaces. So programming against interfaces is one of those mantras that possibly everyone has heard about, right? Everyone knows that we should be programming against interfaces. But why is that relevant in a functional context? Well, the point is that when you program against interfaces, the complexity of an interface stays roughly constant, even if the program or the application that consumes the interface scales indefinitely. Which means that effectively the effort that you have to put in order to understand the piece of code that you are dealing with, that is consuming perhaps an interface, ends at the point of the interface. You don't need to understand what is the implementation behind the interface, which means that effectively, the only thing that really matters is the contract that is represented by the interface. You don't really care about what's happening behind it, which means that, again, you are reducing emergence, you are reducing the mental burden that is required to understand the semantics of the program that you're dealing with. You're changing. And therefore, it makes a lot easier to figure out exactly what you're trying to do or what you need to change and what you need to implement. Okay, so far so good for the first two tiers. Now with the tier 3 stuff, we are going to wander into more advanced territories inevitably. So these are like the techniques that I suggest for more confident teams or for larger projects, whereby for me it makes sense to use these techniques. So, for example, really starting reading through this list. So tackling the expression problem, using anti-corruption layers, and also using perhaps not using to the fullest structured concurrency. So when it comes to tackling the expression problem, so this ties back straight to what we were discussing earlier with the last point for tier 2. So programming against interfaces lends your code to one of the most advanced techniques in the Scala ecosystem. So it's the tagless final pattern of coding. So the tagless final is a design pattern that allows for separate representations of the same expression in different contexts. So what you can see here, for example, is an implementation, first of all, of an interface which is morphic, but then just below, you get a tagless final implementation of the same interface, which abstract over some higher kind of type, which is this known influence, perhaps F type parameter to the trait itself, which essentially does the trick. As in, because of that higher candidate parametricity, we are able to build two different implementations of the same expression of the same interface for two different meanings or for two different scopes. So one is for production code where, for example, one might want to implement this interface using a Fusion in order to leverage all the capabilities of concurrency and parallelism and so on. Whereas instead, for test implementation, for the test code implementation, perhaps one will just want to use option, foregoing completely all the complications that come with the abilities of Fusion of executing in parallel and so forth, right? So the ability of then separating these two representations gives you then a higher level of abstraction while keeping business logic clean and testable. Oh, by the way, sorry, I didn't mention the fact that, I'm not going today into the definition as well as what is the meaning of the expression problem, because it will take a talk on its own, right? So if you have already heard about it, then probably you understand what we're talking about. If you haven't, I would suggest to research some literature because there's plenty anyway, especially when it comes to seeing examples of tagless final implementations. Then another one is using anti-corruption layers. So this builds on top of what we were looking at before, right? Where from using techniques from tier 1, where we are using new types as well as refinement types, we can build definitions that then can be encapsulated into some codec layer, which lives at the boundaries of the application that we are building, and through which we are essentially able to guarantee that's only some value that has some precise and well-defined state goes into the application, perhaps like even come out of the application. And the point is that because of the fact that we're using both new types and refinement types, then we are able to build immutable instances, which also have a very specific semantics, very specific meanings attached to that go into the application, and that can be changed or can be manipulated in any other way, but just consume the values as they are. So that, for example, if you have a JSON codec built using the Serra library that represents, that is able to consume a JSON that represents a person, then only a person that has, again, an age which is positive and a name which is an empty string can be passed in as an input to a possible post person's endpoint in order to create a person within the system. So that guarantees that you don't have any ambiguity and any uncertainty on the state of the values that are coming into the system. And then the last but not least, which is the big one for me, which is the structural concurrency. So in order to look into this topic, I would like to go through a bit of like these quote from Dijkstra's possibly famous go-to statement considered harmful paper, which goes like, we should do as wise programmers aware of our limitations, our utmost best to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program, which is spread out in space, and the process, which is spread out in time, as trivial as possible. And guess what? Well, structured concurrency gives us pretty much that, as in, for example, when you look into using a library or a tool such as CatEffect.io, although it's not really the only one, especially in Scala, that can give us that. But if we look at like a tool such as that, IO has the ability of being lazily evaluated, which means that you only have the execution of the code that is described within your chain of IOs executed only when it's actually explicitly asked. There is no code that executes on its own volition, like, for example, it happens when you use futures, for example, or bare threads. And because of that, you know exactly what happens at each invocation. There is no ambiguity, there is no doubt around what is going to be returned out of this piece of code. It also has the superpower of saving resources by canceling in-flight correlated executions upon failure of cancellation requests, which is, again, another incredible thing that you care about, like how much your company spends when it comes to save CPU cycles, then probably you really want to consider that. And yes, so I think we've come a long way in order to look through, as we said, the theory around what I believe, and will also like these giants that on top of which I stand in order to answer the questions such as what is FP, how do you FP, where do FP? And my answers to these questions are that effectively FP is all about composition, controlling or harnessing emergence, and being able to zoom in and fully understand what a piece of code means without having to, again, have the whole mind map, the whole picture of everything inside and also outside of a system in order to understand its meaning and semantics. And how do I do FP? Well, the answer really to this question depends on your team or how comfortable your team is with these techniques that we described, as well as how big your project and the project that your team works on is. And where do I do FP? Well, really, FP, I think they make sense in any non-trivial project, and really also the size of the project really makes a lot of difference. I think because typically FP makes sense in the large right, where you have like perhaps a lot of code that have to be to make sense together, and you want to keep track at all times of its meanings in all places that is being used. And yeah, I guess that's it. So thank you very much for being with me tonight and listening to my talk. I hope that I said something that was at least interesting for some of you at least, and thank you. Right, so do we have time for questions?
Well, we can take some questions.
Okay.
So why don't we have questions from this room first, and then we'll ask semi-remote attendees. So,
Yes.
questions.
See your example you had for new types and refinement types.
Yes.
Do you have any examples of where you would, because what you're doing was like age and it had a positive end that you
Yes.
defined. What's the difference between like in that example a new type versus refinement type? Because you're saying like there's a new type age that has an end. But like what other, like I guess what's the difference between the two? The way you
Well,
annotate versus
The difference between new types and refinement types is quite fundamental. As in, new types are typically wrappers around what are the either base types or primitive types that live in the JVM, to which you want to attach a very specific piece of information, which means that you want to use that value only in some specific position within your application. So this is what a new type is for. Whereas instead, when you use refinement types, you are taking next step, you are attaching a predicate to that value in such a way that you take that value and you say this value of this type can only have a subset of all the possible values of this type. So the combination of these two is what gives you the maximum of ergonomics, because effectively you can describe a very precise type by combining these two techniques together. So this is where I think it really shines, and not only by using new types alone or refinement types alone, but by using them together. There is also like the extra thing that the new type library in Scala 2 gives you is the fact that the values are effectively mutable, as in it removes completely, for example, the ability of calling the copy function on some instance of a new type, which means that effectively you are basically guaranteed that whatever is the value that is coming through, especially if you've implemented a anti-corruption label, so a codec that is inflating for you this value in some of these new types / refinement types, you have essentially the guarantee that this is actually what you are getting from your caller, from the caller that is calling into your API.
That makes sense.
Cool.
Any other questions?
Thanks for the talk. And then I was quite interested to know like how did you come up with this tier one should be this many and tier two?
Well, that's just an intuition.
Okay.
Completely honest. As in, this is also like part of this talk. Is in none of these ideas that I've been talking about is novel, right? So this intuition comes from the fact that I have like 15 plus years of experience in this industry, and I work with teams with different sizes, and I'm seeing that there are techniques that go more easily down with some teams that have like perhaps less experience, or they have like a smaller set of features that they have to implement, compared to instead where it comes to implementing system that requires perhaps months or even years of development, and the team is like perhaps like large, like 10, 15 developers that are working together on some code base. So based on that, based on the observations that I made over time, I sort of like figure out that this is where like this kind of thing sits.
The only parallel which I can draw is there was this really old article from Martin Odeski in his blog, which had like level A.
Oh, yeah, but
Yeah.
no, I'm not like referring to that. Yeah,
Yeah, that's the only thing which I've like, come across.
yeah, you're right. Actually, I didn't even think of it completely. Yeah, there is no correlation between the two.
Oh,
things.
sure. Okay.
All a brainchild of mine.